Oh. So thank you, Dr. Mithilesh, for a nice introduction. So I will start with sharing the screen. Could you please confirm whether my screen is visible or not?
Yes, sir, it is visible, sir.
Okay. Okay. So first of all, thank you to all the members from OP Jindal University. And Dr. Saroj had been communicating with me, Dr. Mithilesh. He introduced me very nicely. So I'm very thankful to all of them for inviting me to this program. Basically for today's program, our topic is digital twin technology for industrial automation. What I observed is, by and large, this faculty development program is on AI driven robotics and industrial automation. So I decided to choose digital twin because as I understand, digital twin plays a very important role on the industry 4.0. I mean, as we progress with industry 4.0, industry 5.0 and further look forward to further progresses, digital twin plays an indispensable role in that. So I choose to talk on that topic. So before that, I'll just quickly introduce my own institute, my department, and then so probably I don't need to reintroduce myself. So I'm from IIT Bhilai. IIT Bhilai is now situated in a approximately 250-acre land in near to Bhilai, Durg Bhilai. So we have a nice campus coming up. So we have just shifted to our new campus in last 2-3 years back, and before that we were operating from Raipur. So these are a few glimpses of the campus. Coming to the departmental facility, so I'll mostly talk about departmental facility. Our department currently have 12 faculty members working in different domains of mechanical engineering. So among the facilities that we are having currently now is various types of manufacturing facilities are there, in which I would like to take a few names, such as micro machining center, such as laser-based additive manufacturing setups. Two different types of setups we are having currently. We have extensive characterization facilities, which is high temperature tribology and optical profilometries, I mean, different types of microscopy and all these things. So coming to the institute level facilities, our institute is also have established a central instrumentation facility, in which we have advanced NMR, XRT, FESEM, AFM. We have stereolithography setups. We also have a TEM. So we are hoping to build up a very exclusive research facility in the central Indian zone. So hope our listeners will also be able to benefit from this. So this is my personal profile. I'm not repeating this. So directly going on to our content. So we are talking about digital twinning. So what we will do is we are taking six or let's say 5 questions. What is digital twin? Why it is important at this moment? And what is the I mean, if I try to do a technological timestamp, so where we are standing in terms of technology and how we can talk about the implementation. Then we will talk about where or who are the beneficiaries or who are the stakeholders in this development. We will talk about how, so which will be the most important part, how the digital twin can be implemented in few, and then to understand the how better, we will go for few test cases, right? So or case studies. So starting with what is a digital twin? So digital twin is nothing but, so if you just focus on the images in the slides, so you will see the central part obviously is a indicative image showing the digital twin of one turbine, the gas turbine setup. So typically digital twins are nothing but cyber physical system, I mean, creating a cyber physical replica of any physical system, right? So, so what I wanted to show with the other two images. So if you note, probably you can identify the first image. It is a very iconic image from one of the games. I mean, so probably around 20 years back, this game was very popular. So we used to play this. And what I recognize is, so all of these games are nothing but digital twins of a particular environment, right? So a scenario is given to the player, and and based on your actions, some reciprocation is coming. So everything is coming from some database or some programmed input-output system, and depending on that, you can achieve certain objectives. So digital twin is nothing but that. However, so the right side image will tell you a better. So the left side is 20 years back, how the gaming used to look like. Right side is probably in 2020, how it look like. So the interfaces of the game is now being integrated with graphics. So what if we can have our cyber physical system integrated with such kind of graphics and visualization, so that the continuous monitoring of systems is possible? So this is where I mean, I just took an example of our graphics in the gaming situations. However, the same is also being implemented on real-time scenarios or real-time machineries. One of the examples you see almost very frequently is in many of the cars, you see a TPMS, which is a tire pressure monitoring system. So you are connected with a pressure monitoring system that on your display that shows what is the status of the pressure in your tire. If it falls down below a certain value, it gives you a warning that you need to refill your tire. So with air. So these kind of monitoring systems actually integrate your physical system with a cyber system and gives you an idea of how to control it in real time. Right. So I'll just go through here, go through these bullets once. The digital twin refers to a virtual representation we already have discussed. It combines the real-time or historical data. So this is very important, that the digital twin, it has a database. It requires a database coming from the similar or same physical system, and it piles up the data, analyze it, and once the analysis is done, the data model is prepared. It combines the prepared data model with a real-time set of data and does a predictive, creates an environment to take a predictive action, right? The digital twin continuously synchronizes the physical counterpart, allowing the real-time monitoring, analysis, and optimization. So when we are talking about a digital twin, it is not only collection of data or sending out a control signal, but it is automated control signal generation based on the collection of data in the in situ or the real-time data collection. So let us go forward. Why we are talking about digital twin? Because it provides a representation of the operational data. So at any point of time, one of the most important and interesting feature of digital twin is it provides a very good representation. We will see a couple of representations when we talk about one of the test cases where we see a robotic arm being monitored using a digital twin. It takes in the database and it analyzes the whole data. So it creates a historical, it has a historical trend input from the previous data. And it can also, because it has the data backup or database, so it also can identify potential causes of the deterioration in the performance. So all of this we can identify using a digital twin. Support for decision making and optimization for day-to-day operations. This is a very trivial feature of digital twin, and then this is the most handy feature as well. It also identifies any abnormal behavior because it has the complete catalog of different behavior of the system. So it can actually identify if there is any abnormal behavior or some downtime is upcoming, some problems are may be faced by the system. So it can identify that. So it can also model future behavior based on analysis of operational parameters. So we have the operational parameters as input, so it can identify any kind of future behavior. So the starting from the moment we employ some operational features, down the line, if there is any upcoming behavioral abnormality can come into the system, so it can identify that. Predictive maintenance, decision making, particularly agile decision making, long-term strategic decisions can be taken through this or with the help of the digital twin. It also identifies and recommends new interventions and actions. So digital twin is not dependent on a human to ask for some interventions. It itself generates interventions requests to the user, and even if given the authority, it can also take actions at time to time. And it also reduces the dependence on human operator. Thereby, it increases the safety features because it reduces the human machine interaction. So now, when? So what is the juncture of time we are standing and we are talking about digital twin literacy? So obviously, the first block in the digital twin that we are talking about is a sensor machine and control closed loop system. So this is nothing new. However, we are still saying that digital twin is something beyond what we have seen earlier. The reason is that the primary requirement is in a sensor and actuator closed loop. The sensor only takes an action, but it cannot have a previous or historical trends or database with it. It cannot bring in the historical trends or data analytics into the picture. However, in this case or at this moment, what we can see is, yeah. So what we can see is we are standing at a point when we have the buzzwords like IoT, Industry 4.0, data science, AI, ML, big data analytics, 5G communication. So there are various buzzwords across different engineering disciplines. And if we try to now integrate a machine with a computer or a cyber system, so the ease of communication, the ease of integration between the machine, the physical system, and the cyber system has gone up by hundreds of folds as compared to 10 years or 15 years back. So you can say the first image here, I will just. So the first image here shows that our improvement in the different kind of networking. So with the increase of the improvement of the network, it is now really possible to bring in systems or physical systems spread across a shop floor or even across a city or even across a big area and connect it. Yeah. Hello. Yeah. So it is possible to connect them through the digital twin, I mean, through to a cyber system, right? So the physical system and cyber system, the bridging the gap is now much more possible thanks to the different kind of networking developments, the communication developments, and now once the data is connected from the system, it has to be analyzed. That analysis can be done using the AI, ML, data science, and big data analytics. So there are various types of computing, cloud computing is existing, which can actually allow us to achieve that kind of analytics. I'll just shortly come to this point. I'll come to this point in a while. But before that, let us also see. So what is the status? So where we are standing in a situation. I mean, standing in a day where the connectivity and intelligence is governing the situation. We have good connectivity. We have data collection using the sensors, and we have sufficient storage capabilities and analysis capabilities. So therefore, we are having the device connected to a system that works on our data analytics. Further, accessing I mean, these data are definitely being stored in a cloud. So where we are still, where we see our next layer of challenges, the data stored in the cloud has to be accessed by the user, or let's say the user interface, and the different standards can be integrated with this so that this data, when it is accessed, can be compared with the standards, and then with the help of complex analytics, it can be fed back to the system for further control. So this is the next stage where we are already stepping in, but the final target is a complete human intervention free machining manufacturing, where the analytics will be done completely by a cyber system, and because it is also integrated through a network of sensors to the physical system, so it can also acquire data from any point of interest, and then it can implement the actuations as required. Right, so this is the the complete structure of digital twin that we are looking towards. So let us see who or where this digital twin are being introduced, I mean, used or introduced. So what we can see is we have number of connected number of industries or number of sectors where digital twin is coming into picture. Right, so this is typically a data for America, Europe, APAC countries, and as we can see, the APAC countries are a little shorter, a little lower in the use of digital twin as of now. However, the trend in all the cases are actually going up. The most important the applications of digital twin lies in the industry, where we are being able to monitor the manufacturing systems or even computer-based systems. It also has some role to play in the smart city as of now. In the car, in the automotive segment, it has a big role to play. And one of the most crucial role it is also playing is in the health sector, where digital twinning of the patient's body or different parts of the body is being attempted to form, so that the effect of a very critical operation can be already understood beforehand. So the reaction of the body can be comprehended very well. So apart from that, smart agricultural, building architectures, retailing and supply chain management, and even in energy sector, digital twin is coming in a great way. Uh, so, so this is more or less the footprint of digital twin when we look into our today's world. So this is the ecosystem of a digital twin. So let us now look into how the digital twin can be implemented. So this is kind of the ecosystem that we are using to implement a digital twin. So what we have here is we have first a block where the real world system is lying. The real world system is taking actuation comments from some system, from a cyber system. Let us just quickly go back and think about a CNC machine. So there was one point of time where the machine and the computer is just directly connected. The computer provides some actuation comments. It has a basic sensing mechanism, so it can also sense what is happening to the what is the current condition of monitoring, right? So the basic block of CNC now is the computer block is now being replaced with a cyber system that not only is monitoring the current sensing signal. So this sensing and actuation used to create a closed loop. But now what we are doing is we are creating an intervention of supervision by the user. We have a data storage. So the sensing data is not only being monitored and sent back as a control signal, but it is also being stored in a cloud, and it is being accessed by high performance computing. Therefore, it is computing all the data, all the previous instances that has happened in the machine, and it is finding out whether the machine has gone through any kind of anomaly at any particular point set of parameters. Not only the input parameters given to the machine, but also the intermediate sensed parameters. Let's say if we are talking about a CNC machine, so maybe we will talk about speed, feed, depth of cut, and rotational speed. So all of these as input parameters, but then we can have intermediate sensing parameters as force, roughness, vibration in the machine. So all of this can be sensed, and then the event of anomaly can be identified from the historical data. And if any such event is coming up, if the trend goes towards that direction in which any anomaly can come to our machine, the machine can now, based on its analytics and AI present, the module present in the machine cyber system, it can now take a decision whether to stop the machine, whether to change the parameters without to prevent any damage to the machine. So now this whole concept of prediction is basically coming from the idea of digital twin. So in a second phase, what we can do is, because we are having sufficient sensing data, so sufficient data is present. So what we can simply do is we can completely skip the real world system from this loop. We have the digital system present, which is a replica of the real world system. And because of the enormous amount of data it has in store, it can provide responses given a specific input. It can always provide a response that what should be the output. So our digital twin now acts as a can act as a completely independent structure or completely independent system apart from the real world system. We can disjoin these two systems, simply feed the digital system or digital twin system with some information about the machining requirements, and it can tell us whether that is possible to perform in that machine, whether there will be certain damage occurring to the machine if we try to perform that kind of activity, whether there will be any additional requirement of power, additional requirement of materials. So it can provide us all the informations even before we are actually reaching the real world system with the practical material, right? So because of this, from the simple example, we can understand if we are talking about a CNC turning machine and we have a proper digital twin, so with appropriate database, with appropriate analytics, it can very quickly tell us whether a specific size and shape of a material can be machined, whether it will require certain type of toolings, whether what should be the critical machining cycles, the on and off time of the machines. So all of these informations it can generate on its own looking at the past data. So this is an extremely good benefit, because many a times we encounter machines where if we try to do experimentations and if the machine gets damaged, it's really a costly affair to maintain the machine or repair the machine. So with a digital twin, we can always go for a beforehand experience with what can happen in the real world scenario. Obviously, there is a supervision existing in the loop. This ensures that we do not have any over or underestimate of the capacity of the machine. From the initially, the supervision will be required from experienced user. However, this also can be taken into account once enormous amount of data is stored in the system. So where I want to emphasize again and again is data. So what is the amount of data stored? So what is the amount of previous history available with the system is very much important for a good functioning of the digital twin, right? And so now within the ecosystem, now we can identify these following components. It requires a virtual representation. So obviously, we will be able to develop this virtual representation based on the actual dimensions, shapes, and size and functionality of different components in the system. We will collect. There will be the storage of previously collected data, analytical models for that. But apart from that, there will be real-time data collection also, and this data can be compiled and compared with previous instances for further understanding of the or further monitoring of the system. Therefore, after that comes simulation and modeling. So one interesting thing is that the same thing that we are achieving through data modeling can also be achieved through simulation. So now I'm saying that I will be employing a digital twin to understand whether a CNC machine can handle a particular type of job or not. The same thing can also be done using a simulation. If we can create a proper simulation, that is possible. However, the problem with the simulation is the simulation mostly are analytical in nature, and because of its analytical nature, often it's a time-consuming affair to simulate a particular situation and give out the outcomes of that particular situation. So let's say I give the four parameters and I try to estimate the force and all force and roughness and other values, force, moment, roughness, and all these parameters. So what the problem we will face is that if we want to involve all real-time factors into the simulation becomes so complicated that it takes a lot of time. So if we want to use such kind of simulations, it takes, so it is not possible to instantaneously evaluate the real-time data collected. The in situ monitoring and in situ control is loses by a certain amount of lag, or starts to lose by a certain amount of lag, because the simulation is taking some time. So here comes the data analytics. Very easily, what we can do is we can pile up your past usage data, and based on that data, we can have a data model that we will be much faster in predicting the outcomes as compared to the simulation. And furthermore, such kind of models will also not include any assumptions. So typically, most of our numerical simulations or analytical simulations consist a lot of assumptions to simplify the actual situation. But real-time data is always consisting of all these factors. So data model provides much faster and much accurate identification of any system responses, right? So, and therefore we can also talk about life cycle tracking, because we are talking about systems and their behaviors, particularly in terms of over the time deterioration of the system performance. So we can track the lifetime, we can identify the maintenance cycle for a particular machine, and therefore maintain the plant or maintain the system in its best performing condition. And lastly, the decision making and optimization can also be possible. So it is not now necessary that we will provide the feed and depth of cut and speed, all these parameters from outside. But if we have a digital twin, we can simply ask the digital twin that given such and such parameters or such and such informations about the material that I'm going to machine. So what is the suggested or optimized parameter set that will give us the best product quality? So as long as we provide all the informations required regarding a specific decision making, so we can always enable our model to make the decision at a very faster pace, as well as provide us very good optimization in terms of parameters. Now, once again, so to perform a digital manufacturing, digital twin for a manufacturing system, so we need real-time control, we need offline and online analytics both. We need a health check. So this is nothing but comparison of online data with the offline analytics, and then we can do a predictive maintenance, which is nothing but a corrective action taken. So now to do this, so in the intermediate layer, let us see what all informations we will require. We will require about the informations about the human interaction with the machine or the personals involved. We will require the information about the equipment. So under the digital twin, there has to be a representation of the personals or human interface. There has to be a representation of the equipment. Bit by bit, the equipment has to be recreated in its digital form. We need to know the material and its behavior, which also should come as a block in the digital twin, so that our equipment and material interactions can be identified properly. For example, if we are working in a let's say a warehouse. If we are working in a warehouse environment, am I audible?
Yes, sir, you are audible, sir.
Yeah. Okay. So, if we are talking about a warehouse environment where a robotic arm is basically dealing with a stack of material, and in that stack of material we have iron blocks, steel, let's say iron blocks, and some composite blocks, also some blocks made of polymer. So obviously the gripping force that is required with the equipment or the robotic arm is not equal for the iron block as to the polymers. So what we can do is our digital twin with the proper identification of the material can also identify that what should be the appropriate force to hold the material, right? So if it employs the equal force as iron block gripping and lifting, so because until it's lifted, the equipment never gets to know whether what is the actual weight, right? So the material is stacked. So the gripping force is applied first and then it is lifted. So if this equal gripping force is applied on a polymer, maybe our sample will be broken or our workpiece will be broken before it's lifted actually. So therefore, the digital twin should also keep a scope for identification of materials and material properties. It should also have a clear participation from the process and the facilities available, right? So if we are planning to make, so this is coming because if we are creating a specific type of facility, let's say we have one type of pick and drop system, and so that is not capable of handling such a certain type of materials. So we should better understand that our digital twin should know that which material to handle with which equipment, right? So it's not that any equipment can do anything. So when a man and machine is interacting, the human can wisely choose or judiciously select which one is which equipment has to be used or which tool has to be used. The digital twin will require also to have the same amount of capability to identify which process to be employed and what kind of facilities to be taken care of. Apart from that, the environment and the final product outcomes. So monitoring of these two is also very much important because our ultimate target is manufacturing and we want to improve the manufacturing quality. So the quality, the information about the quality of the final product has to go back to our analytics block to make it aware that at a particular parametric set or particular condition of working, what is the outcome we are getting. Right? So this is basically something that we need to observe. Now, coming to a next block, so I'm trying to give an overview of what kind of features should be there present in the digital twin. So we need a cyber physical system based machining. So here, what we are trying to do is we are trying to establish a cyber physical machining, cyber system based machining system. The digital twin technology has to be properly developed. So the whole block of digital twin technology once again consists of analytics, networking, understanding of the system, the physical system, and so once we can do that, we can have IoT enabled real-time data acquisition. So why I bring in IoT here is that the data acquisition has to be appropriate and as detailed as possible. So wherever I want my digital twin to be utilized, or for whichever objective I want my digital twin to be utilized, I need appropriate set of data backing it up. Right? So advanced human machine interactions will be required, but this has to be limited as much as possible, and we need cloud-based solutions because as we understand, for most of the digital twins, it is not possible because we are talking about manufacturing systems digital twin. The shop floor environment is bound to be not compatible with the cyber systems to coexist. So we need to have network of sensor and proper networking arrangement so that the sensor data can be transferred to a cloud where a cloud-based solution can be taken and sent back as a control signal to the system. Right? So we need in the process of developing a digital twin, we need the shop floor technicians from all three categories: the operators, technicians, maintenance technicians, as well as quality control engineers. All three needs to provide their feedbacks, which interacts or which goes as a feedback to our human machine interface, right? So what essentially is done is the shop floor technician's job is modified into a human machine interface, and then further this human machine interface is converted or modified into a cyber twin, right? So with this we can have a working digital twin which works in tandem with a cloud where the data is being saved, and we have a designers and planners which which also takes in the data from cloud and modifies any kind of product requirements. So here comes the complete package where we not only say a current product is being monitored, manufactured and monitored using a digital twin, but also we introduce that our product designing or product modification module inside the digital twin, so that it allows us to evaluate what can be the effect or what could be the consequences of certain modification in the product. So more or less the same thing. So we are talking about the schematic constructions. So here, what we are starting is, I will slowly now move to one of the specific one of the specific test cases. So we will start discussing test case. This slide I'll come back in a minute. Before that, let us just quickly see. Okay, yeah. So the schematic of the digital twin is here. So we have a monitoring unit, we have an analysis unit, we have a simulation unit, and we have a management unit which does the comparison job with the simulation results. So here, this analysis and simulation can be clubbed, as I was discussing. Once we have data analytics, we do not always need the simulation to be true, but we can always have the simulation and compare it with the analysis for better understanding of the system. Now, this gives us characteristic profiles of different kind of machine parameters or data with respect to other outcomes, right? So the information that I'm getting or gaining from the physical system is the materials, dimensions, different process parameters, spindle speed, feed rate, and different codes to operate the system. So all of this is basically brought back, or all of this basically fed back from the physical system to my digital system. Now, apart from that, with correspond to this machine data, we have a sensory data. So this sensory data is nothing but the current, vibration, temperature, acoustic emission, force, and so all of these are measured. Proximities, positions, even so all of these are measured in a real-time basis and send it back. So now, when we try to analyze, we can find corresponding to a specific set of force or vibration, what was the parameter, right? So what was the spindle speed at that very moment when the force was reaching a certain value. So we can have all these mappings within our analytics. And now our analytical block here is capable of giving me an outcome of sensory data without actually consulting the physical machine, because because of the stored data, right? So based on this, now it can provide me a digital diagnosis of the machine behavior, and it also can provide me an optimization of the parameters, right? So let us see in a little more detail. We have various steps to in this process. So we start with identification of the requirements. So this is very much important, because I'm saying that the network of sensors has to be established along with the physical system. So what kind of sensors we incorporate? If we want the surface roughness to be smooth for any particular product, so we provide the measurement of surface roughness, or measurement of vibration, or measurement of force. So we try to identify those parameters or those features of the process that are affecting our target requirement. So first stage is we identify the informations that I need to gather, right? So if we decide that we need a smooth surface, so here I declare that my purpose is to find out or to get a smooth manufactured surface out of a system. Based on that, I identify what are the data needed for this, whether it's a force data, whether it's a tool wear data, whether it's a temperature data. So all of this I find, I identify from my system understanding, and ensure that my sensors are placed within the physical system properly. And we also identify what are the constraints in identification of some of the sensors. So now once this stage is done, in the second stage, we start collecting data, because our sensors are in place now. So these sensors start giving us the data, and we start having the data storage in the cloud. So once the database is formed after certain amount of machining, or certain amount of processing, so this database is used to create a data model, and that model is interfaced with the physical system, right? So now we start building up a virtual representation, because so far what we are talking about is a data model. It will probably generate some plots, some graphs, or some alarms, or some text-based alarms. But what we want is we want a better visualization. So what we can do is we can create the digital model, which is nothing but the CAD model of the whole system, and different parts we can identify with different color codings, or different kind of syntaxes which tell us about the force, temperature in different parts. So I will show it in a while. So this gives us a type of visualization that tells us about the actual machine, right? The network communication and connection securities are also very much important. So this is why it is important is, if because we are using an active communication device to provide the to collect the data and provide the control signal. So once it is done using the internet, the security always becomes a challenge, right? So for that, we need a good communication system with proper security. So we can, once we can establish this, then our data stored through the network communication can come to my visualizing setup, and it can give a proper visualization, as well as it can also be subjected to the analysis. And this analysis block, as we can see in the step 5, there will be different types of analysis. So we can choose different modules of data analysis or data modeling, and those modules will give me the final outcome as our desired outcomes, and those out, I mean, the final predictions, and based on those predictions we can have the decision making or actions. Now, does the digital, I mean, so we also need to understand whether the digital twin is working properly, and whether the digital twin is meeting our purpose or not. So first thing first, if we have to understand the digital twin, whether it is working properly or not, then we need to verify. So what we will do is we will provide certain inputs to the physical system directly, and also the same inputs we will be providing to the independent digital twin system. And if the cyber physical system gives out the same and equal output as the physical system, then we can say that our cyber physical system is now ready. And the second part is validate. So we also need to understand. So the first part, when we are doing a verification, we are not giving a violatory parametric set to our system. We are giving everything within the domain where we are operating. But let's say we want to identify the failure in certain type of failure, and then to validate, we provide the system the parameters that would actually cause that or probably cause certain failures in the system. So I will provide such kind of parameters, and based on that parameter, if the digital twin predicts, yes, it will fail. So we can obviously find out a previous or historical data point that accounts to a failure in our physical system, and whether that same data point also accounts to a failure in the digital twin will give us the proper validation of the process. So here I just had discussed the case study of a computer system. So here what we have is we have a multi-mission computer. So this multi-mission computer is obviously engaged in doing a multi-directional task. Now this is connected with a Ethernet switch to some monitor. So our target is to understand whether this multi-mission computer is continuously on the internet, what the internet activities, how we can monitor, and how we can, I mean, if there is any issue with the internet, internet connections or Ethernet connection, we should be able to understand. So this is nothing but, so if you look into it, this Ethernet connection based system is nothing but the basic system of a digital twin, which connects you to the physical system. You are having your physical system connected to the sensors. These sensors are sending data through either Ethernet or Wi-Fi or any kind of signals, and then you connecting these signals. So apart from having your sensors working properly, you also need to know whether all your data communication portals are working properly or not. So this comes as a very essential part of the digital twin. So what we are doing here, we are creating a replica of the similar components, or with the corresponding physical components are placed in a circuitry, online circuitry, and there we are creating all structures and communication protocol in place, and then we are continuously we are continuously monitoring the amount of data if it can transfer using the digital twin. And at any point of time, if there is any lapse in the communication, our digital twin can continuously let us know how or where it is happening. How we can do that? We can have a data monitor over this Ethernet 1, 2, and 3. So in case the Ethernet 1, 2 both are working, but Ethernet 3 is not working properly, it's not getting certain kind of output. So we can say that definitely the problem is in 3. So this is a way we, from a whole network, we can identify exactly where some problem is coming into picture. So this kind of circuitry and digital twin are extensively used in large size networks where your office networks, where computer internet connection has to be provided. So we can use this kind of communication where a computer system will continuously display that which are the online systems, which are the offline systems, and which systems are not working at this moment. So all of this can be observed through a visual system, right? So here I have just noted some of the processes. I'll just speed up a little because so that we can go for more relevant uh, physical systems. So from this we can actually create an action plan out of the digital twin using proper analysis, as I have discussed already before. So this is the computer-based system. It will provide us the verification of the data, that is, I mean, information that I'm giving. So we have so whether all equipments are installed or not. So it may so happen that my computer is showing that one particular Ethernet is not working because it is not installed properly. So it will do all the checks and ticks, and it will provide me the information about the functioning and non-functioning parts. Okay, so so it has been observed that the downtime or the time when the machine is not performing can be reduced up to 39-40% with the use of digital twin. So in case of automotive factory, where the goals in another case study where the automotive factory, the goals are set as keeping the production line in optimum condition. That means we want a specific flow of output or product. So that is number one. Number two is we want the analysis of different the life and durability of different produced materials, as well as we want the life and durability of our components that are participating in the system. And we need to enable an immediate response when the emergency occurs. So we need to understand the severity of any kind of parametric variations, and then we need to take decision based on that using our digital twin. The testing and managing different scenarios as virtual data can be provided. So let us see how it is being done. So what we are trying to do here is we are identifying 4 verticals. First one is monitoring and analyzing the temperatures of motors in the robotic arm. So what we are trying to do, we have a robotic arm that is participating in activities in a assembly plant, and we are trying to monitor the temperature, because we know that for sure that if the temperature goes beyond a certain point, the effectivity or working ability of the motor falls below. I mean, the productivity starts to go low, and beyond certain temperature, the motor can have severe malfunction. So we have this as one objective. We can have another objective where the dust in the factory environment will be monitored. We can have third objective where the temperature in different factory in the factory environment will be monitored. The outside temperature, ambient temperature will be monitored, and then we can have any kind of frequency or vibration that is present in the system that will be also monitored. Let us see what kind of, so we can have different type of sensors. We can have temperature sensor and dust sensor and then vibration and force sensors. I'm not going into the detail of this, but obviously I would like to stress upon this that this is the specific example. So they have talked about Apache Kafka, which is a specific software. However, what I want to stress upon is Windows open source stream processing platform. This is basically the stream of data is coming to the software, which is being processed continuously and fed back to the system as control signals. We need to handle the real-time data streaming and processing. We need high throughput and low latency, fault tolerance, so low fault tolerance, and then exactly once processing semantics. So what we need is that in our process, we cannot allow any kind of high fault tolerance. We cannot have multiple attempts at the prediction. We cannot say that now the temperature is, because if any time I make a false prediction, either I am losing a product or my product line is. So if I say that my product will be prepared, but it does not prepare because of some false prediction, my product is going bad. Or if I say that no, the product is not going to be made, there is a critical condition, so I'm switching off the system. So I'm losing on the productivity end. So either way, I have some loss, either material loss or productivity loss. So with both sides, we don't want to go. So we need exact once processing semantics as well. Apart from that, we have a virtual simulation platform, which is Unity platform. Unity platform is very well known to create games and interactive experiences and for simulation. So it's basically a virtual visual platform that provides you the understanding of actual the cyber physical system. So let us just skip to here where we can look into the visualization. As you can see here, the robotic arm is now color coded, right? So the color coding is coming because the system you are continuously monitoring in a screen, and if you see your robotics arm is going yellow to red, then you are understanding the temperature in the motors must be going high, because that is basically the robotic arm temperature or the motor temperature mode. Now, second is in case of frequency, you are monitoring certain in your CNC machine, you have a vibration sensor. If the frequency goes up, you can observe. If the environmental temperature is going up, you can observe. So you basically create a virtual scenario in your screen where different sections will show you or alarm you with the temperature rise or the change in the dust density or so these are this data points from different sensors that is coming to your screen. So with this, you can actually see what you can actually observe your digital twin and even can have a manual interface for the control. However, you can further integrate this to automation that if the dust density is such and such, then you will have a dust cleaning equipment or let's say the air purification equipment working at higher capability for certain duration. So you can have the control measures connected to this, and if you give proper authorization to your system, digital twin, it will also perform the control measures as required. So with this experiment, it has been observed that a huge amount of downtime reduction was possible, as well as the working time reduction was also possible by a large amount. So the working time reduction means that the intervention, the same productivity was achieved within a much lesser time as compared to without digital twin. So the observations of the system, identification of downtime in the system or identification of any anomaly in the system. So all of this becomes much easier when you have a digital twin in place. So now coming to the last part and the last case study. So this is a glimpse of our current research. We are working with single point micro incremental forming. So what we are essentially doing is we are using a micro tool. The tool has a round or hemispherical tip. The tool is pressed onto the workpiece material, and through or by virtue of localized deformation, we are creating a sample. So this is a standard SPIF process. Now, for our purpose, what we are using is we are using a high spindle speed. So for the high spindle speed, we are employing a micro machining setup, and the spindle speed can go up to 70,000 to 1 lakh RPM. And we are having a very thin sheet of aluminum, and the micro tool of diameter one of the range of 1 to 2 millimeter we are using to deform the sheet to find out what is the formability of this sheet under certain processing conditions. So our target, then I can very easily identify that my target for this digital twin making or this research is to understand the failure points of these sheets, right? So we are trying to identify at what point of time or at what parameter we will have a failure. So what we did is we started experimenting and then saving the data or saving the information. So two types of information was saved. First, the formability data was collected. Formability data is nothing but so at what point of time or at what depth of such deformation. So the deformation you can see here. So at what depth we will find a crack either in the wall or at the base of the sheet. So if we find a crack, then that means that is the limiting height to which we can deform the part. So this was measured after the experiments and was fed to my data cloud. And during the experiment, continuously the force was measured, the force for deforming in both all X, Y, and Z directions. The moment required to rotate this tool, that was also measured. And post experimentation, we have also measured the roughness in the wall, because our expectation was that the roughness will provide us some information about the failure. So later with those data, so let me also quickly show you what is the experimental setup. This is the micro machining setup that we have in our department. This has the capability of rotating the tool as 1 lakh RPM. And the micro tools are typically of the dimension below 1 mm. But in our case, we are using up to a 2 mm dimension tool, 2 mm diameter tool. We have created a special fixture that can hold a very thin aluminum sheet. The sheet thickness is below 50 micron, and with the help of dynamometer, we are measuring the forces. Post experimentation, we are measuring the height using a optical profilometer. However, the positional information from my tool can also be considered as the height measuring information. The machine has a continuous force measurement system which stops the machine as and when the force goes below certain value. This basically allows us to actively track the failure occurring in the sheet. Right? So whenever the failure is occurring, the machine is stopping automatically. Now, this we continued this research. So this is the tool diameter, exact tool diameter of 1.5 radius, 1.5 mm radius, and this is the fixture. We use this fixture to create the tools, and the geometry, as you can see, is here. We selected few parameters, right? So we were talking about parameters. We selected few key parameters, which are wall angle, spindle speed, feed rate, and step depth, and we selected few steps. So we did experimentation on all of this and then fed this data to my data model, right? So how did we do the data model? We have used a data model. So before that, using the data model, I try to understand what is the correlation between the parameters, which are the important parameters that we need to monitor more closely, right? So what we can see is wall angle is, so these are the outputs. I measured the formability, forming height, forming time, and the surface roughness. So forming time and surface roughness gives me the information about product quality, forming time about the productivity, and forming height and formability about the product capability. So later, when we try to see the effect of different parameters on normalized scale, we see the correlation coefficients are high between wall angle and formability, whereas the feed rate gives us lower forming time, and step depth also gives us, so step depth and feed rate has a negative correlation with the forming time. and has less correlation with the forming height and forming width. So what from here in going forward, what we could do is we could relax the feed rate and step depth from our further modeling, because we know that the correlation between step depth and feed rate when we are looking forward to the forming height is much lesser. They don't have much of the effect on the forming height, so we can relax those, right? So sorry. Yeah, so we use the whole data, and then using this data, what we have done is we try to plot the parametric settings. So this gives us a decent amount of understanding about the process. But our intention, I mean, this gives us the physical understanding of the process. However, our intention was to create a digital twin. So I'll just go forward, and here are some examples of how the surface roughness and the force plots where force was measured. And here, what we did was we created a ML based regression model. We explored around 32 regression models from different structures and architectures, and from which we selected these four. So these four models provided better performance in correlating the parameters with the outputs, right? And then these models were used to optimize the R square and RMSE values with respect to the wall angle, spindle speed, feed rate, and the step depth. So these four parameters was connected with my surface roughness and forming height. The R score and RMSE was used as a matrix to monitor the closeness of feet. When we went forward, we saw that these four are giving at least the QSVM was showing lower R square value, but others were showing very high R square value. So it was showing a very good prediction in for the heights. And so when we were doing this, the total data, 70% of the total data was used to prepare this model, and the rest of the 30% was used for 30%, 20 was used for further training, and 10% was used for the validation of the model. And we saw that our model was decently working, and the prediction of height and surface roughness was possible from the in situ from the parameters. So now, so this is one table that shows the prediction of roughness and the forming time with the given parameters. If the parameters is given to us, the actual value is providing me that I can measure from my physical system is this. However, if I'm using a digital twin that I have created through by virtue of the ML model, that gives us these data, which are pretty close to the actual data, right? So going forward, now, so we will come to the conclusion of this talk now. So the future of digital twin, what we can see is that with the expansion of IoT, we have various version of digital twin technology. So digital twin technologies are being employed various product in various products, and so as the prediction was made, so this was made around 2020. So the prediction was around 2022. 85% of all IoT platforms, wherever we have IoT platforms, we will have 85% of those platforms having some kind of digital twin, which is very obvious because IoT is basically standing on the digitization and cyber physical systems. So we will need digital twin to reach IoT and successful implementation of Industry 4.0. Apart from that, we could also see that as we move towards smart devices, smart products, smart manufacturing, and smart components, so we are basically reinforcing the idea of digital twin. So often what we can think is that digital twin is a wholesome representation of cyber physical system. It may or may not be that. Maybe a part of the physical system is only converted into a cyber physical system just to monitor a specific corner of the process. If I want the wholesome monitoring, then only we need a complete digital twin. So digital twin is not something that has to be achieved completely in one go, and partial achievement has no meaning. It's not like that. So every time when we are creating some monitoring, some data-centric modeling and predictions, and trying to monitor a system, we are basically taking one step towards the digital twinning. And so it is which, looking at the common trend of data analytics and AI ML applications, so it is a it is a worth motivating people that digital twin of systems be made and be implemented in industrial scale, so that the industrial productivity can be improved further. So here are some sources or references. I thank you for your attention, and now I request if you have any queries or questions, so we can discuss.
Thank you so much, sir.
Thank you.
Participants,
Thank
if
you.
you have any query,
Thank you very
may- yes, yes, and
much for this from the resource person. So if you have any query, either you can post the question in the chat box or question and answer section, or you can raise your hand. Sir, I have some questions regarding this.
Yeah, sure.
What industries have adopted digital twin technology most successfully so far, apart from manufacturing? Because I have seen the manufacturing industries are working very hard to adopt this technology to optimize their performance and to improve the efficiency. Recently,
Yes.
I have attended one conference like JSP Tech Catalyst. So in that, I have seen most of the industries are working in this and they are adopting this. So apart from this
Right.
manufacturing industry, what are the different sections or different sectors?
So two of the industries. One is the construction industries, or the building constructions and building planning has been. I mean, digital twin has been very instrumental because so in a building, if you look at it, you have electrical connections, you have water connections, gas supplies, internet connectivity. So all of these, and then because there are multiple stakeholders, you have multiple portals through which these services or benefits are being disbursed. So to make sure that all of these portals are working fine, digital twin is a very good option to actually monitor, right? So building planning and building construction business has been implementing this, if not always in India or in subcontinent, but in US and Europe, there are examples where this has been implemented a lot. And apart from that, medical systems, because often nowadays, I mean, new age operational features are there where doctors can experience the actual situation inside a patient's body in a digital twin without physically physically engaging with the patient, because if doing an actual operation, if there is some mistake, that can be fatal. So the digital twinning of that is also targeted by in a big time.
Okay, sir, we have one question from the participant.
Yeah.
Is this method can be applied to any physical system, or does it have any constraint?
More or less, it can be applied to any physical system, as long as we can select proper network of sensors and we have appropriate analytics tool. So sensors becomes a problem or challenge because the sensors often have a typical lifetime, right? So when we talk about implementation of sensors, and recently we come across monitoring of blast furnace. So what we observed is that the sensors that are placed, so there is a nice practice of digital twin actually there when it comes to monitoring of boiler or blast furnace or coke oven, where the working environment is so harsh that you cannot physically go and check on the condition of the plant. So there are number of sensors, particularly thermocouples, mounted on these plants to monitor. But the problem is that this thermocouples always have certain lifetime, and your actual product, the lifetime is much prolonged. The lifetime that we expect from a plant is around 20 years, 30 years, or even more. The lifetime of thermocouple can be around 7 to 10 years, and after that it often goes not working. So in such cases, we have seen that this becomes a challenging issue to maintain the continuity of the digital twin. Your twin model is working, but your data collection stops. So as long as you can maintain the sensor networks, it is always can be applicable.
Possible.
Yeah.
Okay, sir. So, what is the minimum hardware and software requirement for the installation of this particular setup?
See, for this, I will give you another example. In another research of mine, we were trying to do the crop monitoring. Okay? So crop monitoring can also be a part of digital twinning of the farm. So there we are using. I mean, there are platforms like Google computing platforms are there. I mean, there are free source, not free source. I mean, registration based platform computing platforms available. So nowadays it is not always essential that you need a your personal or your own monitor. I mean the computational system. So you can always borrow the computational power from different computing agencies. So that is also possible. But then sensor network is a always requirement. So that you cannot borrow from others.
Okay, so we have a question from the participants. Given that the real-time synchronization between the physical and virtual entities is fundamental to an effective digital twin, how would you address the issue of temporal drift and data incoherence in distributed digital twin architectures, particularly when integrating multi-scale models involving both high-frequency physics-based simulation and low-frequency business logic across heterogeneous IoT infrastructure operating with asynchronous message passing protocols?
Like MQTT and OP. Okay, yeah. So what I get is that
MQTT and OPC UA and edge to cloud.
okay. So what I get from here is that the problem is that so we have a distributed digital system, digital twin in many cases. So we often have different lead time in transmission of the data. So we need to add certain modules to cope up with this. And so our data model that we are creating, that should have the prediction capabilities, and it should, I mean, that should take into account the lead time of this transmission. So that is the only option that I can see. Right. So your data model should should be trained in a way that it takes a lead. I mean, it can predict 5 seconds. I mean, if your lead time is 5 seconds, your data model should be able to predict some data point 5 seconds in the future, not at the very instant. So it should have that kind of capability.
Sir, I have one question. Like,
Yeah.
is it beneficial for SMEs also, like small and medium scale industries, or it will be always giving benefit to the large industries?
No, as I was telling that digital twin can be done as, I mean, it can also be partially achieved. It's not necessary that the digital twin has to be completely achieved. The wholesome digital twin probably always will be reserved for large players, but partial digital twin can always help us. I started with the example of TPMS in our car. So that way, we do not have a complete digital twin of our car. It's not telling us when some bearing or some bushes are failing. But then at least the day-to-day maintenance part is taken care of through that part of the twinning. That is letting us know that that tire pressure is less, the fuel condition is, I mean, fuel is less, the AC condition is not right. So whichever is our target feature, we can always convert that to a partial cyber physical system, and we can access that.
Okay, thank you, sir.
Thank you.
So I think now we can close the session. Sir, please give me just a minute.
Yeah, sure.
So dear all, everyone, a very good afternoon to all. It is my privilege and honor to extend the vote of thanks on behalf of the Department of Mechanical Engineering, OP Jindal University, Raigad. First and foremost, I would like to express our heartfelt gratitude to Dr. Purnendu Das for delivering such an insightful and enriching session on digital twin technology for industrial automation. Sir, your expert lecture has not only deepened our understanding of this emerging and transformative technology, but also highlighted its practical application and future scope in the field of industrial automation. Your valuable insights on integrating virtual models with real-time systems will surely inspire both our faculty members and students to explore new research directions. We sincerely appreciate your time for this from your busy schedule to share your knowledge with us. Your session has certainly added great value to this faculty development program, sir. I would also like to thank all the participants for their active engagement and thoughtful questions, which made today's session more interactive and meaningful. Once again, thank you all. And with this, we are going to close this session. Thank you, sir. Thank you very much.
Thank you, Pranay.
Thank you very much.
Thanks.
Thank you.